Hello, welcome back. Today we're going to finish to talk about solubility equilibrium. We're going to see some effects that would alter the solubility of ionic compounds, and we're also going to learn how to rank the solubility of different compounds. So the first thing we're going to talk about is the common ion effect. If you remember, we talked already about common ion in the unit about acid-base solutions, and in particular when we talk about the buffer. A common ion tends to reduce the solubility of a compound, and it happens when you have poorly soluble compounds, like for example in this case silver chloride, and you have also the presence of a more soluble compounds, let's say sodium chloride or hydrochloric acid, that shares an ion in common with the precipitate. So in this case the common ion is chloride, of which we have 0.01 molar. So the first thing you want to do is write your solubility product expression, and it's a simple stoichiometry, it's a 1-to-1 ratio, and then we can start working on our IC table. So let's have a look at the dissociation reaction. We can explain the common ion effect in terms of Le Chatelier principle. So basically, because of the extra source of chloride, what was going to happen is that the chloride concentration is going to be higher, and that's going to push the equilibrium towards the reagent. So we're going to have less silver dissolved than we would otherwise have. So basically what you need to remember is that the KSP is a constant, so it's always going to be the same number. The only thing that would change the KSP would be a change in temperature. So if one of the two concentration is different, this will alter the concentration of the other ion. So if we have a lot of chloride, we will have less silver, and that will mean that we will have a less amount of silver chloride solid that's going to be dissolved, and that's why the solubility is going to be decreased. So differently from what we've seen before, now we have that the initial concentration of the chloride is different from 0, because there is already some chloride from a different source. So when we are calculating the solubility, the concentration, at equilibrium, we're going to have two different values. The amount that you get from the dissolution of silver chloride is still going to be the same for silver and chloride, but for silver is adding to nothing. For chloride is adding to some pre-existing amount of chloride. So by plugging those numbers, the two concentration at equilibrium, into the KSP, we are going to obtain, through some simple algebraical passages, this expression. Now this is a second degree equation. To solve this we need to use the quadratic expression, and as you know, I'm not a big fan of that. So is there a way to avoid that? So the solubility of silver chloride is already about a small number, right? Even more so because we have the common ion effect. So we really expect that x to be a really small number. So we can assume that when we're adding x to 0.01, especially if we are actually using proper significant figures, the result is going to be pretty much unchanged. So if we do that simplification in the equation that we have obtained from the other slide, we get a much simpler algebraical expression that we can solve easily. At this point, I would like to take a step back and remind you something that we covered at the very end of the unit about acid-base equilibrium. There was salt hydrolysis. So neutralization, a reaction between an acid and a base that would produce a salt and water. So we can consider the opposite reaction, and that is salt hydrolysis. That's the reaction that you get when you put salt in water and you get back the original acid and base. So we can imagine each salt as derived by the reaction of a parent acid and a parent base. And this is going to help us classifying that salt as acid, acidic, neutral, or basic. So let's see some example. To do this, we need to separate the cation from the anion, so we get sodium plus and chloride ion. and after that you add an OH minus to the cation and you add an H plus to this anion, and in this way you get the parent base and the parent acid. So this is the parent base and this is parent acid. The next step is to classify them as either strong or weak. So NaOH is a strong base, therefore the conjugated acid is going to be extremely weak. Hydrochloric acid is a strong acid, therefore the conjugated base is going to be extremely weak. So NaCl is going to be neutral. In this second example, we're going to see ammonium chloride. We separate the ammonium ions and the chloride ions. We get the parent base, that's ammonia or ammonium hydroxide, and we get the parent acid, that's hydrochloric acid. So hydrochloric acid is a strong acid, its conjugated base is going to be weak, so it's not affect the pH. But ammonia is a weak base, therefore it's going to have a strong conjugated acid, and that will make ammonium chloride an acidic salt. If we have the opposite situation, we are going to get sodium hydroxide as parent base and hydrofluoric acid as parent acid. You remember hydrofluoric acid is weak, is the one used in Breaking Bad to fill the bathtub. We've been talking about that in class. So the conjugated base, that's fluoride ion, is going to be strong, and this will make NaF a basic salt. So when a salt is either basic or acidic, its solubility is going to be affected by the pH. So this is a table that just summarizes different properties depending on the parent base or acid and the effect on the pH of the solution. What is the effect of pH on solubility? So in this example, we're considering a basic salt. Calcium fluoride is basic because the parent base, calcium hydroxide, is very strong. However, the parent acid, that's hydrofluoric acid, is a weak acid, therefore the conjugated base, that's the fluoride, is going to be a relatively strong base. So this equilibrium is the dissolution equilibrium, while this one shows you the equilibrium relative to the hydrolysis of the fluoride. So the fluoride ion can react with the water, forming back hydrofluoric acid and OH-, and these OH- are the reason why the solution is basic. So what happens if we are in the presence of an acid? What's going to be the effect on the solubility of calcium fluoride? Would we manage to dissolve more or less? So in the presence of an acid, the H plus will react with the F minus, forming more HF. As a consequence, the presence of an acid has the effect of reducing the amount of fluoride ions. So the fluoride ions concentration is going to go down. And this is causing, according to Le Chatelier, the equilibrium to shift towards the products. So we are going to see more calcium fluoride dissolved, and therefore the solubility is going to increase. The opposite happens if we have a basic solution. In a basic solution, the OH- is going to have a higher concentration. This is going to move the equilibrium towards the left. The larger amount of F- will move the dissolution equilibrium towards the left. Therefore, less calcium fluoride is going to be dissolved, and the solubility will be decreased. Okay, so let's see an example of a question where you have to predict if you will have a precipitate or not. To do this, you need to calculate Q. So let's remember what Q is. We have been discussing the difference between Q and K in the general discussion about equilibrium. So it's a bit like having a thermostat in your house. The thermostat is set to a specific temperature, let's say 65 Fahrenheit, and that's your K. But then the temperature in the house at any given moment could be any value, and that would be Q. It could be 40, it could be 70, it could be 80, it could be 30. So Q can have infinite value, while K is a very specific value. So whenever Q is equal to K, you are at equilibrium and the situation is at a steady state. Whenever Q is different, something has to happen. For example, the furnace may go on, off, or the windows need to be open so that you can change the temperature until it reaches K. So here is a bit of the same thing. This is the equilibrium solubility for lead chloride with the KSP that's pretty small. The Q is calculated in the same way by multiplying the concentration of lead times the concentration of chloride to the second power. But while Q can have infinite value, KSP can only have one specific value. So by comparing the Q obtained at a certain specific concentration of lead and chloride, you can tell if it's going to precipitate or not. If Q is higher than KSP, you simply have too much ions. The reaction needs to move in this direction, so you will form more precipitate. If Q is too small, you have room for more ions, so you can dissolve more lead chloride and increase the concentration of the ion until you reach this equilibrium value. So let's see an example. We're mixing two solutions, and one contains lead nitrate and the other one contains sodium chloride. And we want to know if we're going to see a precipitate of lead chloride or not. So this is basically a double displacement reaction, the same that you've been seeing in the first semester when you were talking about reaction aqueous solution. So the two possible products are lead chloride and sodium nitrate. Sodium nitrate is going to be very soluble, as all sodium salts are soluble and all nitrate salts are soluble. But lead chloride is what you in Gen Chem 1 would have classified as insoluble. So that's what we are interested in. So first of all, you need to realize that the total volume of the solution is going to be 400 milliliters after we mixed these two. We need to calculate the concentration of lead and chloride at the end of this mixing, so we have numbers to enter into this equation. So the first thing we need to do is transform this in liters, because according to the definition of molarity, molarity is the number of moles per liter. So if we multiply molarity and volume in liters, we get how many moles we have. And then to figure out the actual concentration after the dilution, we will need to divide by the final volume, that's 400 milliliters. So by for example, for lead, by multiplying 0.275 liters times the molarity, we get the total number of moles of lead. This total number of moles of lead is going to be dissolved in a total volume of 0.4 liters. So this gives us 0.0921 as the concentration of the lead after the mixing. So in the same way, we can calculate the concentration of the chloride, and then we can plug those two numbers into the Q formula, and we get a value that is smaller than the KSP. Therefore, we can tell that the precipitate will not form. So finally, let's see how to rank solubility. In this problem, they are asking you to figure out which one of the two has the greatest solubility between magnesium hydroxide and magnesium carbonate by comparing the KSP. Now, you might be tempted to look at this and say, well, the magnesium carbonate has the highest value for the KSP, therefore is also going to have the highest value for the solubility. Unfortunately, this is not the case, and this is because they have different stoichiometry. That means that you actually have to calculate, to make sure, you actually have to calculate the solubility from the KSP, from both of them. And this is something that we've seen how to do before. So you can write the equation for the dissolution of the magnesium hydroxide and calculate the KSP, actually calculate the solubility as X from the KSP, where KSP is equal to 4x cubed. And then you do the same for the magnesium carbonate, in which case KSP is going to be equal to x squared, and you can calculate again the solubility. Now when you compare the solubility, you can see that the highest value is the one for the magnesium hydroxide, despite the fact that his KSP was smaller. So this is an example where just comparing the numbers would have given you the wrong answer. Now let's have a look at this problem where you are asked to compare and rank the solubility of 5 different substances given their KSP. Now, according to what I just told you, you would have to calculate S from KSP 5 times. So that would be a lot of time invested in one exercise. Is there a way we can avoid that? Yes. In this case, we can actually directly compare the values because all those salts share the same stoichiometry. In all instances, the ratio between the cations and the anions is 1 to 1. So the answer is very easy. It's just about figuring out which one has the highest number. That is this. So let's see this example. So these are 3 different salts. Both the cation and the anion has 2 charges, so they're all in a 1-to-1 ratio, and therefore the KSP are going in parallel with the solubility. Whoever has the highest KSP has the higher solubility, whoever has the lowest KSP has the lower solubility. The same in this example where the ratio is 1 to 2. Now, I just want you to pay attention to the fact that it doesn't matter if the ratio is 1 to 2 or if the ratio is 2 to 1, because at the end of the day, you always end up with the same ratio, that KSP is equal to 4x cubed. So it doesn't really matter in terms of ranking. And that's going to be all you will need to know for the KSP. So the next unit is going to be thermodynamic, and we will start by refreshing some notions of thermochemistry that you will cover in Gen Chem 1. Stay safe.